Hello learners, welcome to Rush Learning Hub where we rise, upgrade, shine and achieve success together. I am your mentor and today we are beginning our UGC NET Environmental Science journey with Unit 2, Environmental Chemistry. In this lecture, we will build a strong foundation by understanding the classification of elements, stoichiometry, Gibbs free energy, chemical potential, chemical kinetics, and chemical equilibrium. We will also explore the solubility of gases in water, the carbonate system, saturated and unsaturated hydrocarbons, and radioisotopes. These concepts form the backbone of environmental processes and are frequently tested in the UGC NET examination. So keep your notes ready, stay focused, and let's transform complex chemistry into simple, exam-oriented concepts. Let's begin our journey toward NET success with Rush Learning Hub. Before we begin today's lecture, let's take a quick look at what you will learn and achieve by the end of this session. Today's lecture is the foundation of environmental chemistry, one of the most important units in UGC NET Environmental Science. The concepts we discuss today will help you understand environmental processes, pollution mechanisms, climate interactions, and many advanced topics that appear frequently in the examination. Our first learning outcome is understanding the classification of elements and their environmental significance. Everything around us, including air, water, soil, plants, animals, and pollutants, is made up of chemical elements. In environmental science, elements are classified as major elements, macronutrients, micronutrients, and toxic elements. Understanding their roles helps us explain ecosystem functioning, nutrient cycling, and environmental contamination. You will also learn why some elements are essential at low concentrations but become toxic when their levels exceed a certain limit. Our second learning outcome is stoichiometry and its environmental applications. Stoichiometry helps us understand the quantitative relationship between reactants and products in chemical reactions. Environmental scientists use stoichiometry to estimate greenhouse gas emissions, calculate oxygen demand in water bodies, determine pollutant concentrations, and analyze chemical transformations occurring in nature. This concept forms the basis of many environmental calculations. The third learning outcome focuses on Gibbs free energy and chemical potential. These thermodynamic concepts help us predict whether a chemical reaction will occur naturally and in which direction it will proceed. Environmental processes such as mineral weathering, nutrient transformations, pollutant degradation, and chemical transport are governed by these principles. Understanding these concepts will help you interpret many environmental reactions from a scientific perspective. Next, we will explore chemical kinetics and chemical equilibrium. Chemical kinetics explains how fast a reaction occurs, while chemical equilibrium explains the balance between forward and reverse reactions. These concepts are extremely important in understanding atmospheric chemistry, aquatic chemistry, pollutant degradation, and environmental stability. Many natural systems continuously adjust themselves to maintain equilibrium. Another important learning outcome is the solubility of gases in water and the carbonate system. The interaction between gases and water plays a critical role in environmental processes. Concepts such as dissolved oxygen, carbon dioxide absorption, ocean acidification, and buffering mechanisms are directly connected to gas solubility and carbonate chemistry. These topics are highly relevant for both environmental monitoring and UGC NET examinations. We will also study saturated and unsaturated hydrocarbons. Hydrocarbons are important organic compounds found in fuels, industrial emissions, and atmospheric pollutants. Understanding their structure and reactivity helps explain processes such as photochemical smog formation and air pollution chemistry. Finally, we will discuss radioisotopes and their environmental applications. Radioisotopes are widely used in environmental monitoring, groundwater studies, age determination, and pollution assessment. Concepts such as radioactive decay and carbon dating are frequently asked in competitive examinations and are essential for environmental scientists. By the end of this lecture, you will have a strong conceptual foundation in environmental chemistry and will be better prepared for advanced topics as well as UGC NET examination questions. So stay focused, take notes, and let's begin our journey into the fascinating world of environmental chemistry. Everything in our environment is made up of chemical elements. The air we breathe, the water we drink, the soil beneath our feet, and even living organisms are composed of different elements. However, not all elements play the same role in environmental systems. Based on their abundance, biological importance, and toxicity, elements can be classified into four major categories: major elements, macronutrients, trace elements, and toxic elements. Let's start with major elements. Major elements constitute more than 99% of biological matter. These include carbon, hydrogen, oxygen, and nitrogen, commonly remembered as CHON. These elements are considered the fundamental building blocks of life. Carbon forms the backbone of organic molecules, hydrogen and oxygen are major components of water, and nitrogen is essential for proteins and nucleic acids. In environmental science, these elements are central to major biogeochemical cycles such as the carbon cycle and nitrogen cycle. Understanding their movement through ecosystems helps us explain climate change, nutrient cycling, and ecosystem productivity. Now let's move to macronutrients. Macronutrients are elements required by living organisms in relatively large quantities. These include phosphorus, sulfur, potassium, calcium, and magnesium. Phosphorus is important for energy transfer through ATP and is often a limiting nutrient in freshwater ecosystems. Sulfur plays a role in protein synthesis and atmospheric chemistry. Potassium, calcium, and magnesium are essential for plant growth, cellular functions, and metabolic activities. Deficiency of these nutrients can reduce productivity, while excessive amounts may contribute to environmental problems such as eutrophication. Next are trace elements. Trace elements are required in very small quantities but are essential for biological functions. Examples include iron, zinc, copper, manganese, and cobalt. These elements act as cofactors in enzyme systems and support various biochemical reactions. Although they are required in minute amounts, their absence can disrupt normal biological processes. An important concept for UGC NET is that trace elements can become toxic when their concentration exceeds safe limits. This brings us to the concept of the threshold effect. The threshold effect states that an element may be beneficial or essential at low concentrations but harmful or toxic at higher concentrations. This is one of the most important concepts in environmental toxicology and is frequently tested in competitive examinations. Finally, let's discuss toxic elements. Toxic elements have little or no biological benefit and can cause severe environmental and health problems even at relatively low concentrations. Important examples include mercury, cadmium, lead, arsenic, and chromium. Next are trace elements. Trace elements are required in very small quantities but are essential for biological functions. Examples include iron, zinc, copper, manganese, and cobalt. These elements act as cofactors in enzyme systems and support various biochemical reactions. Although they are required in minute amounts, their absence can disrupt normal biological processes. An important concept for UGC NET is that trace elements can become toxic when their concentration exceeds safe limits. This brings us to the concept of the threshold effect. The threshold effect states that an element may be beneficial or essential at low concentrations but harmful or toxic at higher concentrations. This is one of the most important concepts in environmental toxicology and is frequently tested in competitive examinations. Finally, let's discuss toxic elements. Toxic elements have little or no biological benefit and can cause severe environmental and health problems even at relatively low concentrations. Important examples include mercury, cadmium, lead, arsenic, and chromium. Mercury is associated with Minamata disease. Cadmium causes Itate disease, lead affects the nervous system and cognitive development, while arsenic exposure can lead to skin disorders and cancer. These toxic elements often accumulate in ecosystems and enter food chains through a process called bioaccumulation. As they move through trophic levels, their concentration increases, leading to biomagnification and serious ecological consequences. Let's connect these concepts to real environmental examples. Carbon in the form of carbon dioxide contributes to climate change and global warming. Excess phosphorus entering lakes and reservoirs can trigger eutrophication, leading to algal blooms and oxygen depletion. Iron is essential for life but may stain water and create quality concerns at elevated concentrations. Lead contamination in soil and water poses significant risks to both wildlife and human health. To summarize, major elements form the foundation of life, macronutrients support growth and metabolism, trace elements are essential in small quantities, and toxic elements can cause environmental and health hazards. Understanding these classifications helps us interpret nutrient cycles, pollution pathways, ecosystem functioning, and environmental management strategies. This topic forms the foundation for many advanced concepts in environmental chemistry and is highly relevant for UGC NET Environmental Science. Stoichiometry is one of the fundamental concepts in chemistry and forms the basis of quantitative environmental analysis. In simple terms, stoichiometry is the calculation of the amounts of reactants and products involved in a chemical reaction. It is based on the law of conservation of mass, which states that matter can neither be created nor destroyed during a chemical reaction. This means that the total mass of reactants is always equal to the total mass of products. Why is stoichiometry important in environmental science? Environmental scientists constantly need to answer questions such as: how much carbon dioxide is produced when a fuel is burned? How much oxygen is required to degrade pollutants in water? How much fertilizer contributes to nutrient loading in a lake? How much pollutant is released into the atmosphere from an industrial process? All these calculations depend on stoichiometric principles. Now let's understand the basic steps involved in stoichiometric calculations. The first step is to write a balanced chemical equation. A balanced equation ensures that the number of atoms of each element remains the same on both sides of the reaction. The second step is to convert the given quantity into moles. Chemists use moles because chemical reactions occur according to mole relationships rather than directly by mass. The third step is to determine the mole ratio from the balanced equation. These ratios are obtained from the coefficients present in the chemical equation. The fourth step is to calculate the number of moles of the required product or reactant. Finally, the fifth step is to convert the result into the desired unit, such as grams, kilograms, or tons. Let's understand this with a simple environmental example. Consider the complete combustion of carbon. Carbon reacts with oxygen to produce carbon dioxide. 1 mole of carbon combines with 1 mole of oxygen to form 1 mole of carbon dioxide. Suppose 12 grams of carbon are completely burned in excess oxygen. The molar mass of carbon is 12 grams per mole, so 12 grams correspond to 1 mole of carbon. According to the balanced equation, 1 mole of carbon produces 1 mole of carbon dioxide. The molar mass of carbon dioxide is 44 grams per mole. Therefore, 1 mole of carbon dioxide has a mass of 44 grams. This means that 12 grams of carbon produce 44 grams of carbon dioxide. This simple calculation forms the basis of greenhouse gas estimation and carbon emission inventories used worldwide. Now let's discuss some important environmental applications of stoichiometry. The first application is the estimation of air pollutant emissions such as carbon dioxide, sulfur dioxide, and nitrogen oxides. The second application is the calculation of oxygen demand in water bodies, including biological oxygen demand or BOD and chemical oxygen demand or COD. The three-road application is nutrient loading assessment in aquatic ecosystems, particularly involving nitrogen, phosphorus, and sulfur cycles. The fourth application is greenhouse gas quantification for climate change studies. The fifth application is chemical treatment and wastewater management, where precise chemical dosages are calculated to remove contaminants effectively. Let's now look at a general stoichiometric approach. We begin with the mass of a reactant. Then we convert it into moles. Next, we apply the mole ratio from the balanced equation. After that, we determine the moles of the desired product. Finally, we convert those moles into mass or any other required unit. Always remember these important examination points. First, balance the chemical equation before performing any calculation. Second, use the mole concept throughout the calculation process. Three-road mole ratios are always taken from the coefficients of the balanced equation. And fourth, stoichiometry is equally important for theoretical chemistry and real-world environmental problem solving. For UGC NET, questions may be asked on mole concepts, balanced equations, pollutant calculations, limiting reactants, and percentage yield. Therefore, developing a strong understanding of stoichiometry will greatly improve your ability to solve environmental chemistry problems accurately. To summarize, stoichiometry is the quantitative language of chemistry. It helps environmental scientists estimate emissions, calculate pollutant loads, assess oxygen demand, and understand chemical transformations occurring in natural and engineered systems. Gibbs free energy, represented by the symbol delta G, is one of the most important concepts in thermodynamics and environmental chemistry. It helps us predict whether a chemical reaction or environmental process will occur naturally under constant temperature and pressure. In simple words, Gibbs free energy tells us the direction and feasibility of a reaction. Many environmental processes, such as weathering, mineral dissolution, nutrient cycling, pollutant degradation, and atmospheric reactions, are governed by Gibbs free energy. The mathematical expression for Gibbs free energy is delta G equals delta H minus T delta S, where delta G represents Gibbs free energy. Delta H represents enthalpy change or heat energy. T represents absolute temperature measured in Kelvin. And delta S represents entropy change, which indicates the degree of disorder or randomness in a system. This equation tells us that both energy changes and disorder influence whether a process occurs naturally. Now let's understand the significance of delta G values. When delta G is less than 0, the reaction is spontaneous. A spontaneous reaction proceeds naturally without requiring continuous external energy. For example, cellular respiration, decomposition of organic matter, and many natural weathering processes occur spontaneously. When delta G is equal to 0, the system is at equilibrium. At equilibrium, the forward and reverse reactions occur at the same rate. Although reactions continue to occur, there is no net change in the system. This condition represents a stable state. When delta G is greater than 0, the reaction is non-spontaneous. Such reactions require an external energy source to proceed. Photosynthesis is a classic example because plants require sunlight to convert carbon dioxide and water into glucose. Now let's discuss why Gibbs free energy is important in environmental science. First, it helps us predict whether natural processes, such as mineral dissolution, precipitation, and weathering will occur. Second, it allows us to understand nutrient transformations in soil and aquatic systems. Third, it is widely used in studying pollutant degradation and environmental remediation. Fourth, it helps explain atmospheric chemistry and greenhouse gas reactions. By analyzing delta G values, environmental scientists can determine whether a chemical process is thermodynamically favorable. Let's look at some environmental examples. The first example is respiration. In respiration, glucose reacts with oxygen to produce carbon dioxide and water while releasing energy. Since energy is released, the Gibbs free energy change is negative. Therefore, respiration is a spontaneous process. The second example is mineral dissolution. When calcium carbonate dissolves in acidic water, the reaction often has a negative delta G value. As a result, dissolution occurs naturally under suitable conditions. The third example is precipitation reactions. When dissolved calcium ions combine with carbonate ions to form solid calcium carbonate, precipitation occurs if the Gibbs free energy change becomes favorable. The fourth example is pollutant degradation. Many organic pollutants break down naturally through microbial and chemical reactions because the overall Gibbs free energy decreases during the process. For UGC NET, remember one important principle. Nature always tends to move toward a state of lower Gibbs free energy. This means that spontaneous environmental processes generally occur because they reduce the overall free energy of the system. Also remember that Gibbs free energy depends on both enthalpy and entropy. Temperature plays a crucial role because it influences the entropy term in the Gibbs equation. At equilibrium, delta G becomes 0 and the system reaches stability. Let's summarize. If delta G is negative, the reaction is spontaneous. If delta G is 0, the system is at equilibrium. If delta G is positive, the reaction is non-spontaneous and requires external energy. Gibbs free energy is therefore a powerful tool for predicting the behavior of environmental systems and understanding natural processes. This concept is frequently tested in UGC NET Environmental Science and forms the foundation for thermodynamics, environmental reactions, and ecosystem chemistry. In this section, we will discuss an important thermodynamic concept known as chemical potential, represented by the Greek letter mu or mu. Chemical potential can be understood as the driving force responsible for the movement of matter from one place to another. In simple terms, It describes the tendency of a substance to move, escape, diffuse, or undergo transformation. You can think of chemical potential as being similar to the flow of water from a higher level to a lower level. Just as water naturally flows downhill, matter naturally moves from regions of higher chemical potential to regions of lower chemical potential. This movement continues until equilibrium is achieved. Now, let's understand the scientific definition. Chemical potential is defined as the change in Gibbs free energy of a system with respect to the change in the number of moles of a substance, while temperature and pressure remain constant. Mathematically, chemical potential is represented as the partial derivative of Gibbs free energy with respect to the number of moles. Although the mathematical expression appears complex, for UGC NET, it is more important to understand its physical significance rather than memorizing the equation. The key idea is that chemical potential determines the direction in which matter moves. Whenever there is a difference in chemical potential between two regions, matter will move spontaneously from the region with higher chemical potential to the region with lower chemical potential. This movement continues until both regions have equal chemical potential. At equilibrium, the chemical potential becomes equal throughout the system. Now let's discuss the factors that affect chemical potential. The first factor is concentration. Generally, higher concentration corresponds to higher chemical potential. Therefore, substances tend to move from areas of high concentration toward areas of low concentration. The second factor is temperature. Changes in temperature influence both energy and molecular disorder, thereby affecting chemical potential. The third factor is pressure. Pressure is particularly important for gases. An increase in pressure often increases the chemical potential of gaseous substances. The fourth factor is molecular interactions. Attractive and repulsive forces between molecules can influence how easily substances move within a system. Let's now look at some environmental examples. Consider water movement in soil. Water naturally moves from wetter soil regions, where chemical potential is high, to drier soil regions, where chemical potential is lower. Similarly, contaminants present in soil tend to migrate toward groundwater because of differences in chemical potential. Another example is the diffusion of gases in the atmosphere. Gases move from regions of higher concentration and higher chemical potential toward regions of lower concentration and lower chemical potential. Nutrients in soil solutions also move from areas of higher concentration to areas of lower concentration, making them available to plant roots. Chemical potential plays a crucial role in many environmental processes. It controls diffusion, osmosis, adsorption, desorption, and mass transfer. It helps us understand the movement of pollutants in soil, water, and air. It is also essential for studying nutrient cycling, groundwater contamination, ecosystem dynamics, and biogeochemical processes. For environmental scientists, chemical potential is a powerful tool for predicting the fate and transport of chemicals in natural systems. Now, let's focus on an important UGC NET examination point. If the chemical potential of two regions is unequal, the system is not at equilibrium. Matter will continue to move until the chemical potential becomes equal in both regions. This concept is frequently applied in environmental chemistry, soil science, atmospheric science, and water quality studies. Let's summarize. Chemical potential is the driving force behind the movement of matter. Matter always moves from regions of higher chemical potential to regions of lower chemical potential. The movement continues until equilibrium is reached. Chemical potential is influenced by concentration, temperature, pressure, and molecular interactions. And most importantly, it helps explain how pollutants, nutrients, water, and gases move through environmental systems. Chemical kinetics, one of the most important concepts in environmental chemistry. Chemical kinetics is the branch of chemistry that studies the speed or rate of chemical reactions and the factors that influence those rates. While thermodynamics tells us whether a reaction is possible, kinetics tells us how fast that reaction will occur. This distinction is very important for UGC NET examinations. A reaction may be thermodynamically favorable, but if it proceeds extremely slowly, its environmental impact may not be observed immediately. Let's begin by understanding the concept of reaction rate. The rate of a reaction is defined as the change in concentration of reactants or products per unit time. In simple terms, it measures how quickly reactants are converted into products. The standard unit of reaction rate is moles per liter per second. A fast reaction has a high reaction rate, while a slow reaction has a low reaction rate. Now let's discuss the rate law expression. The rate law establishes a mathematical relationship between reaction rate and reactant concentration. For a general reaction, the rate can be expressed as rate equals K multiplied by the concentration of reactant A raised to the power m multiplied by the concentration of reactant B raised to the power n. Here, K is known as the rate constant. The values of m and n are called reaction orders and are determined experimentally. The sum of these powers gives the overall order of the reaction. Understanding reaction order is important because it helps us predict how changes in concentration affect reaction rates. Let's now examine different orders of reaction. In a zero-order reaction, the reaction rate remains constant and is independent of reactant concentration. The rate equals K. In a first-order reaction, the reaction rate is directly proportional to the concentration of one reactant. The rate equals K multiplied by A. In a second-order reaction, the rate is proportional to the square of the reactant concentration. The rate equals K multiplied by A squared. For UGC NET, you should be familiar with the characteristics and graphical representation of these reaction orders. Now let's discuss the factors that affect reaction rates. The first factor is temperature. As temperature increases, molecules gain more kinetic energy and collide more frequently. As a result, reaction rates generally increase. The second factor is concentration. Higher reactant concentration increases the probability of molecular collisions, leading to faster reactions. The third factor is the nature of reactants. Some substances react rapidly, while others react slowly depending on their chemical structure. The fourth factor is pressure. Pressure is particularly important in gaseous reactions. Increasing pressure effectively increases gas concentration and therefore increases reaction rates. The fifth factor is the presence of catalysts and inhibitors. Catalysts increase reaction rates by lowering activation energy, whereas inhibitors slow down reactions. Finally, surface area also influences reaction rates. Finely divided solids react faster because more surface area is available for interaction. Let's now explore the temperature effect through the Arrhenius equation. The Arrhenius equation explains how temperature affects reaction rates. According to this equation, the rate constant increases exponentially with temperature. As temperature rises, a greater number of molecules acquire sufficient energy to overcome the activation energy barrier. Consequently, the reaction proceeds faster. This principle explains why many environmental reactions accelerate during warmer conditions. Now let's connect chemical kinetics to environmental processes. One important example is photochemical smog formation. Smog forms through a series of atmospheric reactions involving nitrogen oxides, volatile organic compounds, and sunlight. The rate of these reactions depends on temperature, light intensity, and reactant concentration. Another example is the decomposition of organic matter. The breakdown of leaf litter, sewage, and other organic materials depends on microbial activity, temperature, oxygen availability, and moisture content. Atmospheric oxidation reactions are also governed by chemical kinetics. For instance, sulfur dioxide can be oxidized into sulfuric acid, contributing to acid rain formation. The speed of this transformation depends on catalysts, humidity, and atmospheric conditions. Similarly, the degradation of pesticides and other pollutants in soil and water follows kinetic principles. Environmental scientists use kinetics to predict pollutant persistence and environmental recovery times. Now let's discuss a few important examination points. Reaction rate and equilibrium are not the same. Kinetics tells us how quickly equilibrium is reached, whereas equilibrium tells us the final state of the system. Catalysts increase the rate of a reaction but do not change the position of equilibrium. Environmental reactions are often complex, involving multiple steps and intermediate products. For UGC NET, questions frequently appear on factors affecting reaction rates, reaction order, catalysts, Arrhenius equation, activation energy, and environmental applications of kinetics. Let's summarize. Chemical kinetics is the study of reaction rates. The rate of a reaction depends on concentration, temperature, pressure, catalysts, surface area, and the nature of reactants. The Arrhenius equation explains the relationship between temperature and reaction rate. Chemical kinetics helps environmental scientists understand pollutant degradation, atmospheric chemistry, nutrient cycling, and ecosystem processes. Understanding kinetics allows us to predict not only whether a reaction will occur, but also how quickly it will influence the environment. Chemical equilibrium. Many chemical reactions occurring in nature are reversible. This means that the products formed can react again to produce the original reactants. When such reactions occur in a closed system, a special condition may eventually be reached where the forward and reverse reactions occur at exactly the same rate. This condition is known as chemical equilibrium. Chemical equilibrium is defined as the state in which the rate of the forward reaction becomes equal to the rate of the reverse reaction. At equilibrium, the concentrations of reactants and products remain constant over time. However, it is extremely important to understand that the reaction has not stopped. Both forward and reverse reactions continue simultaneously. Therefore, chemical equilibrium is called a dynamic equilibrium, not a static one. Consider the simple reversible reaction. A reversibly forms B. Initially, the concentration of reactant A is high, so the forward reaction proceeds rapidly. As product B accumulates, the reverse reaction begins to increase. Eventually, both reactions occur at the same rate and equilibrium is established. Now let's discuss the two major types of equilibrium. The first is homogeneous equilibrium. In homogeneous equilibrium, all reactants and products exist in the same physical phase. A common example is the Haber process. Nitrogen gas reacts with hydrogen gas to form ammonia gas. Since all substances are gases, this is a homogeneous equilibrium. The second type is heterogeneous equilibrium. In heterogeneous equilibrium, reactants and products exist in different physical phases. A classic example is Calcium carbonate solid decomposing into calcium oxide solid and carbon dioxide gas. Because solids and gases are involved together, this represents heterogeneous equilibrium. Now let's move to one of the most important principles for UGC NET examinations, Le Chatelier's principle. Le Chatelier's principle states that whenever a system at equilibrium experiences a disturbance, the system shifts in a direction that opposes the disturbance and attempts to restore equilibrium. This principle helps us predict how equilibrium responds to environmental changes. Let's examine some common disturbances. First, change in concentration. If the concentration of a reactant increases, the equilibrium shifts toward product formation. If the concentration of a reactant decreases, the equilibrium shifts toward reactant formation. For example, when atmospheric carbon dioxide increases, more carbon dioxide dissolves in water, shifting equilibrium toward carbonic acid formation. Second, change in temperature. Temperature affects equilibrium differently depending on whether the reaction is exothermic or endothermic. An increase in temperature favors the endothermic direction, while a decrease favors the exothermic direction. This principle explains many atmospheric and aquatic chemical processes. Third, change in pressure. Pressure mainly affects gaseous equilibria. When pressure increases, equilibrium shifts toward the side containing fewer moles of gas. This is an important concept frequently tested in competitive examinations. Fourth, change in volume. A decrease in volume effectively increases pressure and can shift equilibrium accordingly. Now let's examine the environmental applications of equilibrium. One of the most important applications is the carbonate buffer system. Natural waters contain carbon dioxide, carbonic acid, bicarbonate ions, and carbonate ions in equilibrium with one another. This system helps maintain stable pH levels in lakes, rivers, groundwater, and oceans. Another application is ocean acidification. As atmospheric carbon dioxide levels rise, more carbon dioxide dissolves in seawater. This shifts equilibrium toward carbonic acid formation, lowering ocean pH and affecting marine ecosystems. Chemical equilibrium also controls many atmospheric reactions. The formation and destruction of ozone, sulfur compounds, and nitrogen compounds are governed by equilibrium processes. In soil systems, nutrient availability depends on equilibrium between dissolved nutrients and mineral phases. This directly influences plant growth and ecosystem productivity. Now let's discuss a very important NET examination fact. At equilibrium, delta G, or Gibbs free energy change, becomes zero. This indicates that the system has reached maximum stability under the given conditions. Remember this statement carefully because it is frequently asked in UGC NET examinations. Many students mistakenly think equilibrium means reactions stop completely. This is incorrect. At equilibrium, reactions continue, but the forward and reverse rates are exactly equal. Let's summarize. Chemical equilibrium is a dynamic state where the rate of the forward reaction equals the rate of the reverse reaction. Concentrations remain constant even though reactions continue. Equilibrium may be homogeneous or heterogeneous. Le Chatelier's principle explains how systems respond to disturbances such as changes in concentration, temperature, pressure, and volume. Environmental processes such as carbonate buffering, ocean acidification, atmospheric chemistry, and nutrient cycling are governed by equilibrium principles. And most importantly, at equilibrium, Gibbs free energy change is equal to zero. Solubility of gases in water and Henry's law. Many gases present in the atmosphere continuously interact with natural water bodies such as oceans, lakes, rivers, and groundwater. Examples include oxygen, carbon dioxide, nitrogen, methane, sulfur dioxide, and ammonia. The extent to which these gases dissolve in water is controlled by a fundamental principle known as Henry's law. Henry's law states that at constant temperature, the concentration of a gas dissolved in a liquid is directly proportional to the partial pressure of that gas above the liquid. Mathematically, Henry's law is expressed as C is equal to kH times P, where C is the concentration of dissolved gas, kH is Henry's law constant, and P is the partial pressure of the gas above the liquid. This equation tells us that when the partial pressure of a gas increases, its solubility in water also increases. In simple terms, the greater the amount of gas pressing on the water surface, the more gas dissolves into the water. Now let's understand the factors affecting gas solubility. The first factor is pressure. According to Henry's law, solubility increases with increasing partial pressure. For example, carbon dioxide remains dissolved in soft drinks because it is stored under high pressure. When the bottle is opened, pressure decreases and carbon dioxide escapes as bubbles. The same principle applies in natural water systems. The second factor is temperature. Unlike solids, the solubility of most gases decreases with increasing temperature. As temperature rises, gas molecules gain kinetic energy and escape more easily from water. This is why warm water generally contains less dissolved oxygen than cold water. This concept is extremely important in aquatic ecology and water quality management. The third factor is the nature of the gas and solvent. Different gases have different solubilities. Carbon dioxide and ammonia are highly soluble in water, whereas nitrogen is relatively less soluble. Now let's examine some important gases that follow Henry's law. Oxygen dissolves in water and supports aquatic life. Carbon dioxide dissolves and participates in the carbonate buffering system. Nitrogen contributes to nitrogen cycling processes. Methane, a greenhouse gas, can dissolve in aquatic ecosystems and sediments. Sulfur dioxide dissolves readily and contributes to acid rain formation. Ammonia is highly soluble and influences water quality and nutrient dynamics. Let's discuss the environmental significance of gas solubility. The first application is dissolved oxygen, often abbreviated as DO. Aquatic organisms depend on dissolved oxygen for respiration. If dissolved oxygen levels become too low, fish kills and ecosystem stress can occur. Temperature and pressure directly influence dissolved oxygen concentrations. The second application is carbon dioxide uptake by oceans. The world's oceans absorb a significant portion of atmospheric carbon dioxide. This process helps regulate Earth's climate. However, increased carbon dioxide dissolution also contributes to ocean acidification. The third application is greenhouse gas exchange. The movement of gases between the atmosphere and water bodies affects global climate processes. Henry's law helps scientists estimate gas exchange rates and carbon budgets. The fourth application is wastewater treatment. Aeration systems are designed using principles of gas solubility. Oxygen is introduced into wastewater to support microbial degradation of pollutants. Now let's discuss deviations from Henry's law. Henry's law works best at low concentrations and moderate pressures. However, some gases show deviations at very high pressures or when strong chemical interactions occur. Examples include ammonia, sulfur dioxide, hydrogen chloride, and carbon dioxide under certain conditions. These gases may react chemically with water, causing deviations from ideal behavior. For UGC NET examinations, remember the following important points. At constant temperature, gas solubility is directly proportional to partial pressure. Increasing pressure increases gas solubility. Increasing temperature generally decreases gas solubility. Cold water contains more dissolved oxygen than warm water. Henry's law is widely used in environmental monitoring, aquatic ecology, wastewater treatment, and climate studies. Let's summarize. Henry's law explains the relationship between gas pressure and gas solubility in water. Gas solubility increases with pressure and generally decreases with temperature. The concept is essential for understanding dissolved oxygen, carbon dioxide absorption, ocean acidification, greenhouse gas exchange, and water quality management. The carbonate system. The carbonate system is often called the natural buffering system of water because it helps maintain a stable pH in lakes, rivers, groundwater, and oceans. Without this buffering mechanism, even small additions of acids or bases could cause drastic changes in water chemistry, affecting aquatic life and ecosystem health. Let's begin by understanding what the carbonate system actually is. The carbonate system consists of a series of reversible chemical reactions involving four major species. Carbon dioxide, represented as CO. Carbonic acid, represented as HCO. Bicarbonate ion, represented as HCO. And carbonate ion, represented as CO superscript 2. When carbon dioxide from the atmosphere dissolves in water, it reacts with water molecules to form carbonic acid. Carbonic acid is a weak acid and partially dissociates into bicarbonate ions and hydrogen ions. Further dissociation of bicarbonate produces carbonate ions and additional hydrogen ions. The sequence of reactions can be represented as: carbon dioxide plus water forms carbonic acid. Carbonic acid dissociates into bicarbonate and hydrogen ions. Bicarbonate further dissociates into carbonate ions and hydrogen ions. These reactions are reversible and remain in dynamic equilibrium. This equilibrium allows the system to respond to changes in acidity and alkalinity. Now let's understand why this system is called a buffer. A buffer is a system that resists sudden changes in pH when acids or bases are added. Suppose an acid enters a lake and increases the concentration of hydrogen ions. The carbonate system responds by converting carbonate ions into bicarbonate ions, thereby consuming excess hydrogen ions. As a result, the pH change is minimized. Similarly, if a base is added, bicarbonate ions react with hydroxide ions to form carbonate ions and water. Again, the pH remains relatively stable. This ability to neutralize both acids and bases is known as buffer action. Now let's examine the distribution of carbonate species at different pH values. At low pH values, below approximately 6.3, carbon dioxide and carbonic acid dominate. At intermediate pH values, between about 6.3 and 10.3, bicarbonate becomes the dominant species. At high pH values, above approximately 10.3, carbonate ions dominate. For UGC NET examinations, remember this important fact. Bicarbonate ion is the dominant carbonate species in most natural freshwater systems. This is one of the most frequently asked questions in environmental chemistry. Now let's discuss buffering capacity. Buffering capacity refers to the ability of water to resist pH changes. Maximum buffering occurs in the pH range where bicarbonate ions are abundant. Therefore, natural waters with high bicarbonate concentrations are generally more resistant to acidification. This buffering property protects aquatic ecosystems from sudden environmental stress. Another important concept is alkalinity. Alkalinity represents the acid neutralizing capacity of water. It is primarily determined by the concentration of bicarbonate, carbonate, and hydroxide ions. In most natural waters, bicarbonate contributes the largest share of alkalinity. High alkalinity generally indicates greater buffering capacity and greater resistance to pH fluctuations. Now let's discuss the environmental significance of the carbonate system. The first application is pH stability. The carbonate system maintains stable pH conditions that are essential for aquatic organisms. The second application is ocean acidification. As atmospheric carbon dioxide concentrations increase, more carbon dioxide dissolves in seawater. This shifts the carbonate equilibrium toward carbonic acid formation and increases hydrogen ion concentration. As a result, ocean pH decreases. This phenomenon is known as ocean acidification. Ocean acidification reduces carbonate ion availability and negatively affects corals, shellfish, and other marine organisms that rely on calcium carbonate structures. The third application is water quality management. Environmental scientists use carbonate chemistry to assess alkalinity, hardness, and buffering capacity of natural waters. The fourth application is geological processes. The carbonate system controls the dissolution and precipitation of calcium carbonate minerals. Processes such as cave formation, limestone weathering, and mineral scaling are closely linked to carbonate equilibrium. Let's also consider some real-world examples. In oceans, the carbonate system regulates seawater pH and acts as a major reservoir of inorganic carbon. In lakes and rivers, carbonate buffering protects aquatic ecosystems from acid rain and sudden pH changes. In groundwater systems, carbonate reactions influence mineral solubility and water chemistry. In soils, carbonate buffering affects nutrient availability and plant growth. Now let's focus on important net examination points. Remember the sequence. Carbon dioxide converts to carbonic acid. Carbonic acid converts to bicarbonate. Bicarbonate converts to carbonate. Also remember the approximate dissociation constants. pK is about 6.35. pK is about 10.33. Most importantly, bicarbonate ions dominate in natural freshwater systems. Let's summarize. The carbonate system consists of carbon dioxide, carbonic acid, bicarbonate ions, and carbonate ions. It acts as the natural buffering system of water and helps maintain pH stability. Bicarbonate is the dominant carbonate species in most natural waters. The carbonate system controls alkalinity, buffering capacity, water quality, and ocean chemistry. It plays a critical role in aquatic ecosystems, geological processes, and climate regulation. In this section, we will discuss an important group of organic compounds known as hydrocarbons and understand the difference between saturated and unsaturated hydrocarbons from an environmental science perspective. Hydrocarbons are organic compounds composed exclusively of two elements, carbon and hydrogen. They are the major constituents of fossil fuels such as natural gas, petroleum, crude oil, coal, and many industrial chemicals. Hydrocarbons play a crucial role in energy production, industrial development, atmospheric chemistry, and environmental pollution. Based on the type of carbon-carbon bonds present, Hydrocarbons are classified into two major categories: saturated hydrocarbons and unsaturated hydrocarbons. Let's first understand saturated hydrocarbons. Saturated hydrocarbons, also known as alkanes, contain only single carbon-carbon bonds. Since all available carbon bonding positions are occupied by hydrogen atoms, these compounds are called saturated. The general formula of alkanes is CnH2n plus 2. Examples include methane, ethane, propane, and butane. Methane is the simplest hydrocarbon and is the primary component of natural gas. Saturated hydrocarbons are generally stable and less reactive because single bonds require more energy to break. They undergo combustion reactions to produce carbon dioxide, water, and energy. Now let's discuss unsaturated hydrocarbons. Unsaturated hydrocarbons contain one or more multiple bonds between carbon atoms. These multiple bonds may be double bonds or triple bonds. Unsaturated hydrocarbons are further classified into two groups: alkenes, which contain at least one carbon-carbon double bond, and alkynes, which contain at least one carbon-carbon triple bond. The general formula of alkenes is CnH2n, and the general formula of alkynes is CnH2n2. Examples include ethene, propene, ethine, and propyne. Because of the presence of multiple bonds, unsaturated hydrocarbons are generally more reactive than saturated hydrocarbons. These bonds readily participate in addition reactions and atmospheric oxidation processes. Now let's compare saturated and unsaturated hydrocarbons. Saturated hydrocarbons contain only single bonds and are relatively stable. Unsaturated hydrocarbons contain double or triple bonds and are more chemically reactive. Saturated hydrocarbons burn more completely under ideal conditions, whereas unsaturated hydrocarbons are more likely to participate in atmospheric photochemical reactions. From an environmental perspective, this difference is extremely important. Now let's discuss the environmental significance of hydrocarbons. The first significance is energy production. Hydrocarbons serve as the primary source of energy worldwide. Petroleum, natural gas, coal, gasoline, diesel, and liquefied petroleum gas are all hydrocarbon-based fuels. The second significance is air pollution. Incomplete combustion of hydrocarbons releases pollutants such as carbon monoxide, soot particles, volatile organic compounds, and polycyclic aromatic hydrocarbons. These pollutants contribute to poor air quality and health problems. The third significance is photochemical smog formation. Unsaturated hydrocarbons and volatile organic compounds react with nitrogen oxides in the presence of sunlight. These reactions lead to the formation of ozone, peroxyacetyl nitrate, and photochemical smog. Photochemical smog is a major urban environmental problem. The fourth significance is greenhouse gas emissions. Methane, which is a saturated hydrocarbon, is one of the most powerful greenhouse gases. Its global warming potential is significantly higher than carbon dioxide over a shorter time period. Methane emissions originate from wetlands, rice fields, livestock farming, landfills, and natural gas leakage. The fifth significance is toxicity and human health. Certain aromatic hydrocarbons, particularly benzene and polycyclic aromatic hydrocarbons, are toxic and carcinogenic. Long-term exposure may increase the risk of cancer and respiratory disorders. Now let's discuss some important environmental examples. Methane is released from wetlands, landfills, and agricultural activities. Ethene is produced naturally by plants and is also emitted from industrial processes. Benzene is commonly associated with petroleum refining, vehicle emissions, and industrial pollution. Polycyclic aromatic hydrocarbons, often called PAS, are produced during incomplete combustion of fuels and biomass. These compounds are persistent environmental pollutants. For UGC NET examinations, remember these important points. Alkanes are saturated hydrocarbons containing only single bonds. Alkenes contain double bonds. Alkynes contain triple bonds. Greater unsaturation generally means greater chemical reactivity. Methane is the most important hydrocarbon from a climate change perspective. Volatile organic compounds contribute to photochemical smog formation. Benzene and PAS are environmentally significant toxic pollutants. Let's summarize. Hydrocarbons are compounds made only of carbon and hydrogen. Saturated hydrocarbons contain single bonds and are relatively stable. Unsaturated hydrocarbons contain double or triple bonds and are more reactive. Hydrocarbons are important energy sources but also contribute to air pollution, climate change, smog formation, and environmental toxicity. Understanding their structure and behavior is essential for environmental monitoring and pollution control. An important area of environmental chemistry that frequently appears in UGC NET examinations. Radioisotopes are isotopes of elements that possess unstable atomic nuclei. Because of this instability, they undergo a natural process known as radioactive decay, during which they emit radiation and transform into more stable forms. Unlike ordinary stable isotopes, radioisotopes continuously release energy in the form of radiation until stability is achieved. These unique properties make radioisotopes extremely useful tools in environmental science, geology, hydrology, ecology, and pollution studies. Let's first understand the basic concept of radioactive decay. An unstable parent nucleus emits radiation and gradually transforms into a daughter nucleus that is more stable. The three major types of radiation are alpha radiation, represented by alpha particles. These consist of 2 protons and 2 neutrons. Alpha particles have low penetration power but high ionizing ability. Beta radiation, represented by beta particles. These are high-speed electrons or positrons emitted from the nucleus. Beta particles have moderate penetration and moderate ionizing power. Gamma radiation, represented by gamma rays. These are high-energy electromagnetic waves. Gamma rays possess very high penetration power but lower ionizing ability compared to alpha particles. For UGC NET examinations, remember this sequence. Penetration power gamma greater than beta greater than alpha. Ionizing power alpha greater than beta greater than gamma. Now let's discuss one of the most important concepts associated with radioisotopes, half-life. Half-life is defined as the time required for half of the radioactive atoms in a sample to decay. Each radioisotope has a unique half-life that remains constant under normal environmental conditions. It is independent of temperature, pressure, and chemical reactions. This characteristic makes radioisotopes valuable tools for dating and environmental tracing. Let's look at some important radioisotopes used in environmental studies. Tritium or hydrogen-3 has a half-life of approximately 12.3 years and is widely used in groundwater and hydrological studies. Carbon-14 has a half-life of approximately 5,730 years and is used for radiocarbon dating of organic materials. Phosphorus-32 is commonly used in nutrient cycling and ecological studies. Sulfur 35 is used to investigate sulfur transformations in ecosystems. Cesium-137 and strontium-90 are important environmental contaminants originating from nuclear activities and are widely used in pollution monitoring. Now let's explore the environmental applications of radioisotopes. The first application is water tracing and hydrology. Radioisotopes help scientists determine groundwater movement, recharge rates, residence time, and mixing patterns. Tritium is particularly important for tracing groundwater flow. The second application is age dating. Carbon-14 dating is one of the most widely used techniques for determining the age of fossils, archaeological materials, and organic remains. Environmental scientists also use radiometric dating to study sediments and geological formations. The third application is nutrient cycling studies. Radioisotopes such as phosphorus-32 and sulfur-35 help track nutrient movement through ecosystems. These studies improve our understanding of nutrient dynamics and ecosystem productivity. The fourth application is erosion and sedimentation studies. Radioisotopes such as cesium-137 can be used to estimate soil erosion rates and sediment deposition patterns. This information is valuable for watershed management and land conservation. The fifth application is pollution monitoring. Radioactive tracers help identify pollutant sources, transport pathways, dispersion mechanisms, and accumulation zones. They provide valuable information about environmental contamination processes. The sixth application is food chain and ecological studies. Scientists use radioisotopes to investigate nutrient transfer, bioaccumulation, and biomagnification within food webs. These studies help assess ecological risks associated with contaminants. Now let's discuss the advantages of radioisotopes. Radioisotopes are highly sensitive tracers. They can be detected even at extremely low concentrations. They provide quantitative information about environmental processes. They are useful in complex systems where conventional methods may be ineffective. And they allow long-term monitoring of environmental changes. However, radioisotopes also have certain limitations. Improper handling may pose health hazards. Specialized instruments are required for detection and analysis. Radioactive waste management can be challenging. And strict safety protocols must always be followed. For UGC NET examinations, remember these important facts. Radioisotopes are unstable isotopes that undergo spontaneous decay. Half-life is the time required for 50% of radioactive atoms to decay. Carbon-14 is used for dating organic matter. Tritium is used in groundwater studies. Gamma radiation has the highest penetration power. Alpha radiation has the highest ionizing power. And radioisotopes serve as powerful tracers in environmental investigations. Let's summarize. Radioisotopes are unstable isotopes that emit radiation during radioactive decay. Their unique properties make them valuable tools for dating, tracing, pollution monitoring, hydrological studies, ecological research, and environmental assessment. Understanding radioisotopes helps environmental scientists investigate processes that would otherwise be difficult to observe directly. With this topic, we successfully complete Lecture 1, Fundamentals of Environmental Chemistry.